Welcome to section 9.2. This section focuses on polar equations and graphs. We are going to identify and graph polar equations by converting to rectangular equations, graph polar equations using a graphing utility, test polar equations for symmetry, and graph polar equations by plotting points. All of these things will help us get a really good idea of what they look like on a graph. And the cool thing about using polar equations is polar graphs are circular. So it's really cool to see these things happening on a circular graph. I highly recommend everyone getting into Desmos, get the app, or go online to desmos.com. Their graphing utility is amazing, and it's super useful to be able to graph these things and see them as they're meant to be. Sometimes our graphing calculators struggle with showing us the full graph because it keeps it in the rectangular graph. Okay, let's jump in. Example 1. Here we're going to transform our polar equation to a rectangular equation and draw the graph. So we have r equals -3 sine theta, and some things that we want to remember is r squared equals x squared plus y squared, and we see sine theta there, so remember that y is what's going to call out that sine theta. So we have r equals -3 sine theta, and if we want to use r squared and we also need r times sine theta, I'm just going to multiply everything by r. And we've done that in an example before. So we'll have r squared -3r sine theta. Now we can change some things out. R squared we can rewrite as x squared plus y squared. And then we have -3, r sine theta, we can rewrite as y. Now if we add 3y to both sides, we'll have x squared plus y squared plus 3y equals 0. That's our equation. And if we graph it, it gives us a circle. And our circle is going to look something like this. Terrible circle. Something like that, and it goes down to -3. So, there we go. Okay, now let's identify and graph each polar equation. The process on these is going to be very similar. Some of the things that I would really like for you to take from this section are being able to recognize by the general forms of these equations what they will make. For example, when I see 3 plus 3 cosine, I can recognize this as the cardioid form. All of the forms of the equations are broken down in your textbook very nicely with examples and of what the equations will look like, and also examples of what they will look like graphically. So it's really nice to see these things and how they affect each other. So the first thing we're going to do is find out how is it symmetrical, if it's symmetric at all. The first one we're going to look for is the polar axes. So, is this symmetric about the axes? So what we do is we replace theta with -theta. And if it comes out as the same equation, then it is. And if it doesn't, then it might not be. So we have r equals 3 plus 3 cosine of negative theta. And remember, cosine of negative theta is cosine theta. So 3 plus 3 cosine theta is what we end with. It's the same. So what we can say is our graph is symmetric with respect to the polar axes. And then we check the line theta equals pi over 2. This, we replace theta with pi minus theta. And this is going to give us r equals 3 plus 3 cosine. And then we're going to have pi minus theta. So that will be 3 plus 3. And whenever we have cosine of a number minus a different number, then we can rewrite it using our trig identities. If you don't remember the trig identities for the sums and differences inside of the trig functions, please review those. That's how you're going to do each of these following examples. So cosine of pi minus theta, we can rewrite as cosine pi cosine theta plus sine pi sine theta. Now, let's simplify this. Cosine of pi is -1. So we're left with negative cosine theta, and sine of pi is 0. So plus 0. This gives us 3 minus 3 cosine theta, which fails the test. So it might not be symmetric to the line theta equals pi over 2. It might not be. What we do know is that it is symmetric to the axes. The last thing we're going to check is the pole. So we replace r with -r. So -r is 3 plus 3 cosine theta. This gives us r is -3 minus 3 cosine theta, which is a fail. Fails that test. So the other thing we can check for this one is if we replace theta theta plus pi. And so that would be r equals 3 plus 3 cosine theta the theta is going to be theta plus pi. And so that will give us 3 plus 3, and we have cosine of theta plus pi. So using our trig identities, we can say cosine theta cosine pi minus sine theta sine pi. This will give us 3 plus 3 times, and cosine of pi is -1, so negative cosine theta, and sine of pi is 0, so -0. This gives us 3 minus 3 cosine theta, which is not our original equation, so it doesn't pass either way. So this is telling us the graph, it might not be symmetric with respect to the pole either. So in order to graph this guy, we're going to need to, we know where it's symmetric with respect to the polar axes. And let's get some points that will give us a good idea of what's happening. So for this one, since it is symmetric with respect to the polar axes, we're going to go from 0 to pi. So 0, we'll look at pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi. And we want to know at these different values what's happening to our graph. 3 plus 3 cosine theta. And if we plug in 0, then we'll just get out 6. If we plug in pi over 6, that gives us about 5.598. If I plug in pi over 3, that gives me about 4.5. If I plug in pi over 2, that gives me 3. If I plug in 2 pi over 3, that gives me 1.5. And if I plug in 5 pi over 6, I get 0.402, and at pi I get 0. So these are approximations. If you feel more comfortable leaving them in exact forms, so if you just leave the radicals in there, that's totally fine. Whatever you're more comfortable with, this just gives us an idea. We can plot them. If you plot out all your points, double check it on Desmos, you should be getting our cardioid, which funny enough is a heart shape. Cardioid. Something like that. And it's in between 4 and 6. And then I think our farthest point out might be -1. So it's something like that. That's just my approximate graph. Okay, next up, we're going to have to move everybody down. We have r equals 2 minus 3 sine theta. We should be able to recognize that this is a limacon. I'm not sure if I mispronounced that, I apologize, with an inner loop. So what we're looking at is almost the cardioid, but it has an inner loop going on. Let's check polar axes first. So we're going to have r equals 2 minus 3 sine of negative theta, which gives us 2 plus 3 sine theta. So that's a fail. If we check the line, pi over 2, then we will have r equals 2 minus 3 sine, and we're replacing it with pi minus theta. So we follow the same as before, rewriting it sine of pi minus theta using our trig identities would be sine pi times cosine theta minus cosine pi times sine theta. And if we find out sine of pi and cosine of pi, this would reduce to 2 minus 3 times sine theta, and 2 minus 3 sine theta is our function. That's what we started with. So this tells us it's symmetric with respect to the line theta equals pi over 2. So that's where we're symmetric. It's important. And let's check the pole. So if we have negative r, that's going to give us r equals negative 2 plus 3 sine theta, which is a fail. So let's replace theta with theta plus pi. R equals 2 minus 3 sine theta plus pi. That will give us 2 minus 3. Let's use our trig identities. Sine theta times cosine pi plus cosine theta times sine pi. And then we find out what is cosine of pi and what is sine of pi, so that way we can have 2 minus 3 times negative sine theta. And that's 2 plus 3 sine theta, which was not our function, so it's telling us it might not be symmetric with respect to the pole. Again, I like to get points so that way I have an idea of what's happening as I'm moving around the graph. So I'm going to go from negative pi over 2 to pi over 2 because we are symmetric with respect to the line pi over 2. So as long as I can find from negative pi over 2 to positive pi over 2, I know it's symmetric. So I only have to find one side. So theta will go from negative pi over 2, negative pi over 3, negative pi over 6, 0, pi over 6, pi over 3, pi over 2. And at these values, we're looking at 2 minus 3 sine theta. So at pi over 2, or at negative pi over 2, it's 5. At negative pi over 3, it's 4.598. At negative pi over 6, we have 3.5. At 0, we have 2. At pi over 6, 0.5. At pi over 3, negative 0.598. And at pi over 2, negative 1. So, what does this look like on our graph? Well, it has the cardioid shape with an inner loop. Something like that, but way better. Yeah, that'll just have to be the best. Our highest looks like 1, it goes out, we hit it at 2, negative 2, our highest, farthest out point should be a 3, negative 5 is down here, so we've got, and so we should recognize this is without the inner loop. And so now we can check for, we get a general idea of what it looks like. We can check for where is it if it is symmetric. And so let's check the polar axes. So we get r equals 4 minus 3 cosine negative theta. That will be 4 minus 3 cosine theta. Because remember, when we have cosine negative theta, it's the same as cosine theta. And so this is symmetric with respect to the polar axes. Next, we'll check our line pi over 2. We will replace our theta. So we have r equals 4 minus 3 cosine, and then we'll have pi minus theta. Use our trig identities. We have 4 minus 3, and we have cosine pi, cosine theta, plus sine pi, sine theta. That will give us 4 minus 3, and then a negative cosine theta. So that gives us 4 plus 3 cosine theta. So that's a fail. Our other check on this would be if we plug a negative r and a negative theta. So negative r equals 4 minus 3 cosine negative theta, which would give us negative r 4 minus 3 cosine theta. So r would be negative 4 plus 3 cosine theta, which is still a fail. And the last thing we want to check is the pole. So we have negative r equals 4 minus 3 cosine theta, and we already checked that, so that's a fail. So it might not be symmetric to the line theta equals pi over 2. And we have one last thing we check on the pole. I almost forgot. Okay, so if we have r equals 4 minus 3 cosine, and we replace theta with theta plus pi, then we'll rewrite that with our trig identities. So we have cosine theta, cosine pi, minus sine theta, sine pi. This will reduce to 4 minus 3 times negative cosine theta. So 4 plus 3 cosine theta, still a fail. Okay, so not symmetric with respect to the pole. If we... I'm gonna have to move everybody down. Okay, so if we get some points going, theta will look from 0 to pi. So 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi. And we're looking at what's happening to our graph, so that's r equals 4 minus 3 cosine theta. At 0, it's just 1. At pi over 6, we have 1.402. At pi over 3, we have 2.5. Pi over 2, 4. 2 pi over 3, 5.5. 5 pi over 6, 6.598. And pi is 7. And plotting some points, getting our symmetry, we have something that looks like maybe like that. Looks like it's going through at 4 and negative 4, 1 right there, negative 7 right there. All right, we have more space to do all of our activities. Okay, so now we're going to look at r equals 5 sine of 2 theta. We should recognize this as a rose. And looking at how this function is set up, we can also recognize it has 4 petals. Being able to recognize these things from what you see in the function is extremely helpful because it gives you an idea of what your graph's going to look like, and then as you start graphing it, if it's not following what you saw, then you should know that you need to double check something. Let's check our symmetry at the polar axes. So we have r equals 5 sine of 2 times negative theta. Now the way sine works with negative theta, it becomes negative sine theta. So this will give us negative 5 sine 2 theta. That's a fail. So it might not be symmetric with respect to the polar axes. Let's check our line. Theta equals pi over 2. We'll have r equals 5 sine 2, and we're going to replace it with pi minus theta. This gives us 5 sine 2 pi minus 2 theta. Use our trig identities. 5, we'll have sine 2 pi cosine 2 theta minus cosine 2 pi sine 2 theta. If we simplify that, we'll get negative 5 sine 2 theta, which is a fail again, so might not be symmetric to the line. Pi over 2. Let's check the pole. We have negative r is 5 sine 2 theta, so that would give us r is negative 5 sine 2 theta. That's a fail. Let's check the one last test. R equals 5 sine. We'll have 2 instead of theta. We're going to have theta plus pi. So that will give us 5 sine 2 theta plus 2 pi. Use our trig identity. We have 5. We'll have sine 2 theta, cosine 2 pi, cosine 2 theta, sine 2 pi. So that gives us 5 times sine 2 theta. Once we find out those values there, that's our starting equation. So this tells us it's symmetric with respect to the pole. Let's grab some coordinates to plot to get an idea. We'll go 0, pi over 6, pi over 4, pi over 3, and pi over 2. And we're looking at where r equals 5 sine 2 theta. So if we plug in 0, we get out 0. If we plug in pi over 6, that's a 4.33. If we plug in pi over 4, that's a 5. If we plug in pi over 3, 4.33. And pi over 2 gives us 0. So it's looping all the way back around to itself. And it looks really awesome. It's such a cool graph. We've got something going on like this. Going out to the 4s. Our beautiful little rose. Next up, r equals 4 cosine 5 theta. Again, we should recognize this as a rose. But this time, given this different setup of our function, we can see that it has 5 petals. Depending if it's even and odd, it changes how we determine how many petals it might have. Let's check our symmetry. Polar axes, r equals 4 cosine 5 times negative theta, and cosine negative theta is cosine theta, so 4 cosine 5 theta. So that tells us it is symmetric. With respect to the polar axes. Let's check our line. Theta equals pi over 2. So we have r 4 cosine 5 times pi minus theta. 4 cosine 5 pi minus 5 theta. Use our trig identities. We have cosine 5 pi, cosine 5 theta, sine 5 pi, sine 5 theta. And simplifying that, we should have negative 4 cosine 5 theta. So that's a fail. That tells us it's not symmetric, or it might not be symmetric over the line. Pi over 2. And let's check the pole. Negative r 4 cosine 5 theta. That would be r equals negative 4 cosine 5 theta. So that's a fail. The other test we have is r equals 4 cosine 5 theta plus pi. That'll give us 4 cosine 5 theta plus 5 pi. Trig identities, 4 times cosine 5 theta, cosine 5 pi, minus sine 5 theta, sine 5 pi. We've got 4, negative 4 cosine 5 theta. So that's another fail. So might not be symmetric with respect to the pole. Now we are going to look through some points. Thetas, we'll look at 0, pi over 6, pi over 4, pi over 3, and pi over 2. So at 0, we're looking at r equals 4 cosine 5 theta. So we're going to have at 0, we get out 4. At pi over 6, we get negative 3.46. At pi over 4, we get negative 2.83. Pi over 3, we get 2, and pi over 2, we get 0. And based off of the symmetry, it's symmetric with respect to the polar axes, we're going to have something happening like this, where we're going to have 5 petals coming off of it. And my sketches of these graphs are just so ugly. And it goes out to the 4s. But it's something like this. Desmos does a way better job than I do. Okay, and our final identifying graph that we'll do is r squared equals 16 sine 2 theta. We should recognize lemniscate, I think is how we say it. It's a Greek word, I don't know. All right, we'll check the symmetry first. We have the polar axes to look at first. R squared equals 16 sine 2 negative theta. So we will see negative 16 sine 2 theta. So that's a fail. The other test we could do is negative r and negative theta. 16. Oh, no, we did negative theta. Sine, 16 sine 2. And instead of theta, we'll put pi minus theta. This will give us r squared equals, if we do r 2 pi minus 2 theta, we'll use our identities here. This gives us 16 sine 2 pi cosine 2 theta cosine 2 pi sine 2 theta, which gives us negative 16 sine 2 theta. Still not, so it might not be symmetric around the polar axes. Let's check our line. Theta equals pi over 2. We'll have r squared equals 16 sine 2 pi minus theta. This will give us something we've already checked. Then we've got another test we could try for this one. If we plug in negative r and negative theta at the same time, which is what I wanted to do earlier, but it wasn't for the right test. This one will give us r squared equals negative 16 sine 2 theta, so that's also a fail, unfortunately. So might not be symmetric with respect to the line, pi over 2. Last thing, let's check the pole. We got negative r squared equals 16 sine 2 theta, which is r squared equals 16 sine 2 theta. And so this tells us it's symmetric with respect to the pole. Awesome. And so let's get some points. Theta and r squared equals 16 sine 2 theta. And also we're going to calculate what r is, because we know what r squared is. We want to know what r is. So we'll look at 0, we'll look at pi over 6, we'll look at pi over 4, we'll look at pi over 3, and pi over 2. At 0, we're going to have 0, and the square root is going to be 0. At pi over 6, we have 13.856, and the square root will be plus and minus 3.72. At pi over 4, we'll have 16, which gives us plus minus 4. At pi over 3, we get 13.856 again, plus or minus 3.72. And at pi over 2, we have 0, which is, square root is also 0. And so our graph should be coming to look something like that. A lot smoother though. Something like that maybe. And we've got like 1 and 2, something like that. Always double check your work with the graphing calculator in Desmos. I really highly suggest them. They've put together a really great program in it. It's very helpful. And our last example for this one is the polar equation for this graph is either r equals a plus b cosine theta or r equals a plus b sine theta. A and b are both positive. Select the correct equation and find the values of a and b. So basically we're applying everything that we know in order to find out what the equation is. So we should recognize what this is. This is a lemicon with an inner loop. And this tells us some of the points that I see are a 1. Let me get a brighter color. I see a 1 going on. I see a 1 here going on. I see a 2 here. Up here I see a 3. So those are some important points that I see. And this tells me that my A is 1. So it's either going to be r equals 1 plus b cosine theta or r equals 1 plus b sine theta. Since this is symmetric, with respect to the line y equals pi over 2, then it must pass the test for that. So let's check each of these. Let's check the first one, r equals 1 plus b cosine theta. This means we have to plug in pi minus theta. So 1 plus b cosine pi minus theta. That's gonna give us 1 plus b trig identities, cosine pi, cosine theta, sine pi, sine theta. This gives me 1 plus b. Actually, it's going to be 1 minus b cosine theta. And it's not what we started with, so that's a fail. So let's check the sign. R equals 1 plus b sine theta. This is going to be 1 plus b sine pi minus theta, 1 plus b trig identities, sine pi, cosine theta minus cosine pi sine theta. Then we've got 1 plus b sine theta, and that passes. So we know that it is the sine version. Also, according to the general form of this equation, we know that b must be greater than a. So what I'm going to do is I'm going to test out what is r1 plus 2 sine theta look like. I plug that into Desmos, it matches our graph perfectly, and so that is where we'll stop.